Good evening, everyone. I welcome you all to the Student Research Seminar series. My name is Divyani, and I will be the host for the evening. This is a monthly event where we aim to showcase the work done at IISc publicly. So, let's get started. For the records, so we would like to know how many of you are IEEE members. So, I would request you to raise your hand so that we can get a count. Okay. Okay. Okay, you can unraise yourself. Okay. Thank you. So let's start today's seminar. Our first talk is on an energy efficient probabilistic broadcast mechanism for ad hoc networks by Vinay Kumar. Now, Vinay received his BE honors in electrical and electronics engineering and MSc in mathematics from BITS Pilani. He is currently pursuing PhD from Department of IEEE-IISc. He was a recipient of Cisco PhD fellowship between 2015 to 2020. His research interests lie in areas of random graphs, percolation theory, and distributed algorithms on networks. Welcome, Vinay, and you can start your presentation.
Thanks, Devyani. Let me share my screen.
Sure.
Is it visible? Is my screen visible?
Yes, it's coming up. Yeah, it's visible.
Yeah, all right. Okay, firstly, thanks to the IEEE-IISc Communication Society for giving me this opportunity to present this work here. So this is mostly the final part of my PhD that I'll be presenting. So it's on the energy efficient probabilistic broadcast mechanism for ad hoc networks. So it's joint work with Naveen Kashyap in the EC department and Yogeshwaran at the Indian Statistical Institute. Yeah. So let me begin with the motivation for my talk. Yeah, for this, let's suppose you have a field in which there are some sensor nodes deployed. So these could be like temperature or humidity sensors which are deployed in the field, and these form a network. Let's further suppose that there's a particular node designated as the source, which has some information that it wants to broadcast. This could be like updating the sensing frequency of the nodes or any other information. So an alternate application that you can have in mind is that of the Internet of Things. So in this scenario, a particular source node would want to do, say, over there programming of the IoT nodes in the whole network. So in both these scenarios, we want to essentially broadcast information in the network. But there are some constraints. So what are the constraints? The constraints on the nodes are that they are energy constrained, they have no knowledge of the network topology, and they have limited computational ability. So in order to account for these constraints, any broadcast algorithm that we propose must be completely distributed and it should run in finite time. All right. So in this talk, I'll be mostly interested on large and dense networks, and I'll assume no interference or packet loss. So what I mean by this is whenever a node transmits, each of its neighbors, one hop neighbors will receive the packet. There won't be any loss in the network. So a naive algorithm for broadcasting is what is called as flooding. So let me explain this flooding mechanism using this small graph of 4 nodes where the yellow node is the source, which has 2 packets, packet 1 and 2 with informations x and y. So in flooding, whenever a node receives a packet, it transmits it to all its neighbors blindly. So and this it does to each of the packets. So here, since we have 4 nodes and 2 packets, there are totally 8 transmissions in the network. Alright. So if you look at the flooding mechanism on a large graph, so here I have a large graph and the plot here is of the number of transmissions and it gets updated with time. So let me resume the simulations. So yeah, so this is a graph of 101 nodes and there are 2 packets, packet 1 with information x, packet 2 with information y. So if you have a graph on n nodes and the source has k data packets, The total number of transmissions is k times n. So we have 101 nodes and 2 packets, therefore 202 transmissions. Moreover, if you have a connected graph, then all the nodes receive both the packets, and hence the fraction of receivers is 1. All right. So, but there is a drawback of this particular mechanism, that there are many redundant transmissions in the network, unnecessary transmissions in the network. So, for example, a particular node might receive the same packet from multiple neighbors, and yeah, so these are wasteful. These basically consume energy of the sensor nodes that we have. So we want to avoid this. So an alternative that has been proposed in the literature is what is called as probabilistic forwarding. So let me explain this again using that small graph of 4 nodes that we had before. Here again you have the 2 packets x and y. In probabilistic forwarding, the source transmits to all its neighbors. Every other node in the network tosses a coin with probability p and transmits it further if it lands heads. If it lands tails, it does not forward the packet. Okay, and this is done independently by each of the nodes to each of the packets. So yeah, so here notice that there are just 6 transmissions corresponding to the yellow nodes, but however, all the nodes have received both the packets. Okay, so we have saved on the number of transmissions. If you look at the simulation on the large graph, this looks something like this. So here the forwarding probability P is chosen to be 0.8. So all the yellow nodes are those that receive the packet and transmit it. The blue nodes are those which receive the packet but do not transmit it. And the red nodes are those which do not receive the packet at all. Alright. So for example, this blue node does not forward the packet once it receives from this yellow node, and hence all the nodes here do not receive the packet. And so likewise with this blue as well. So more generally, if you have a graph on n nodes with k data packets and packets are forwarded with probability p, then the expected total number of transmissions is upper bounded by k times n times p. Why is this so? Let's assume that all the nodes have all the k packets. So the source has k data packets. So let's assume that all the nodes have k data packets. Since each node transmits a packet with probability p, on an average, n times p number of nodes transmit a particular packet, and since there are k packets, there are k times n times p number of transmissions. However, this is an upper bound because we assume that all the nodes have all the k packets, that is, all the nodes receive all the k packets, which may not be so, which can be seen from this simulation here. All the red nodes do not receive the packet at all. So here notice that the number of transmissions is 147 compared to 202 which you had for flooding. So we have saved on the number of transmissions, that is, we have saved on the energy. However, the problem with this mechanism is that the fraction of receivers is just 0.693. That is, so even if a particular node does not receive at least one of these 2 packets, then it has not received the information from the source. And hence, if you omit all the red nodes here, you will obtain this fraction of receivers to be 0.693. Alright. So our aim is to actually improve upon these fraction of receivers, but at the same time keep the number of transmissions to a minimum. Okay, so in this direction, we propose a new algorithm called as probabilistic forwarding with coding. So let me go back to that small graph example to explain this. So here again, you have these 2 packets, x and y, and the same probabilistic forwarding mechanism happens. Source transmits to neighbors, every other node tosses with probability p. However, in this situation, both these nodes toss tails, and the node on top does not receive the packet 2 with information y. So in such a scenario, what the source does is it encodes a third packet and does the same probabilistic forwarding. It transmits to all its neighbors. Every other node in the network tosses a coin with probability p and then forwards it if it lands heads. Notice that any node in the network which receives at least 2 out of these 3 packet transmissions is able to recover both x and y. Okay. So here again, you have 6 transmissions corresponding to the yellow nodes. However, all the nodes in the network have received at least 2 out of the 3 packet transmissions. Okay. Yeah, so here again, if you look at a simulation of this, so here again I have 3 packets x, y and x plus y. Notice that the forwarding probability now is 0.72. before it was 0.8. So I have decreased it. This is because there is an additional packet which can be received by nodes in the network as well. Okay. So here the total number of transmissions is 161, and the fraction of receivers is 0.861. So, but what are these fraction of receivers? These are those nodes which receive at least 2 out of these 3 packet transmissions. That is, those nodes which are either yellow or blue in at least 2 out of these 3 packet transmissions. Those are collected and indicated as green nodes here. So this fraction is 0.861. So what we want to see is how much can we push this. So here notice that the number of transmissions is actually more than what we had for probabilistic forwarding, where it was 147. So we want to see how much we can push this. That is, so the only reason that we have been able to obtain or we have been able to decrease this forwarding probability is because we have an additional coded packet. We want to see whether if you add further coded packets, can you bring down this forwarding probability to be much lesser? That is, so because of that, you can decrease the number of transmissions, but at the same time, you can keep this fraction of receivers to be high. All right. Say if you wanted the fraction of receivers to be 0.693 as we had in the previous case, you can actually bring this down much further. All right. So we want to characterize this phenomenon that we are observing. So let me explain this probabilistic forwarding with coding mechanism a bit more formally before I proceed. Um, yeah. So yeah, essentially what is happening is the source has encoded packets, and this encoding is such that any node in the network which receives at least k out of these encoded packets, it's able to recover the information from the source. All right. There are many codes in practice which have this particular property. For example, maximum distance separable codes, fountain codes, etc. Now, once the source does this kind of an encoding, how does the broadcast mechanism work? The source transmits all the encoded packets to its one-hop neighbors, and every other node in the network transmits with probability p and does nothing with probability 1 minus p. Each packet is forwarded independently of other packets and other nodes, and subsequent receptions of the same packet are neglected. All right. Uh, yeah. So now with this, yeah, I mean, before I move, probably it's good to take any questions if they are there about the mechanism, forwarding mechanism. I'll pause for a couple of seconds. Okay. Yeah, so in some previous work, we had actually characterized this on deterministic graphs, such as when the underlying graph is a grid, or when the underlying graph is a binary tree with the root being the source, and other lattice structures. However, for the applications that we are interested in, say of the sensor network or of the Internet of Things network, these are usually modeled using random graphs, specifically random geometric graphs. So let me first explain what these random geometric graphs are and then describe what our goal is. So a random geometric graph, I'll refer to them as RGGs, is parameterized by an intensity parameter lambda. Okay. So how do you generate a random geometric graph on in some area, on an m by m area around the origin, gamma m? First, you select the number of points you want to have. That is, you select a Poisson lambda times the area of gamma m, which is m square. Okay, so you get from this you get the number of points. Now, once you have the number of points, how do you how do you put them in gamma m? You choose them uniformly and independently within gamma m. Okay, so something like this. So these form the points of a Poisson point process, which we call phi. All right, and these constitute the vertex set of the random geometric graph. Now, once you have the vertices, you can place edges between nodes which are within unit distance of each other to obtain the underlying random geometric graph, and it will look something like this. All right. And now that you have a graph, okay. Now that we have a graph, can we do probabilistic forwarding on this? Well, not exactly. I need to tell you where the source is. So what we do is, in our formulation, we add an additional point at the origin and call that to be the source. Alright. So what this means is that we'll be operating on a new point process phi0, which is the original point process along with the origin. Okay. So we'll call this resultant graph to be denoted by GM0. Also, what this means is that all our computations has to be done with respect to what is called as the palm probability. So this palm probability formalizes this notion of probability given that there exists a point at the origin. Uh, yeah, so for our purposes, it suffices to think of this palm probability as the distribution of this phi0 point process. However, a formal description of this requires the ideas from Radon-Nikodym and the derivatives, so I won't get into that. For our purposes, it suffices to think of this palm probability as the distribution of this new point process phi0. Okay. Okay, now that we have a source, now can we do probabilistic forwarding? Well, there is another technical issue. We don't know whether the graph is connected. So we simply chose these n vertices uniformly within gamma m, and however, we don't know if the graph is connected. I have actually here shown a graph which is connected, but it may not be so. So in order to overcome this, we'll employ the probabilistic forwarding with coding mechanism on this component of the origin. So all those nodes which are connected to the origin, so that will form a subgraph of this GM0, and we'll be employing the probabilistic forwarding on this graph, on this component of the origin. So in a practical scenario, what does this mean? Say, let's take the example of the sensor network that we had. So there, you can think of a user entering the field with his mobile phone wanting to broadcast information to all the nodes in the network. So who can he broadcast the information to? He can only broadcast the information to all those nodes which are reachable to him. That is, all those nodes which have a path to him or which are in the component of the user. Any broadcast algorithm that he uses, he can only broadcast it to those guys, to those nodes. Okay, so this is the intuition behind making this kind of an assumption. That is, we employ the probabilistic forwarding mechanism on the component of the origin. Okay, so now that we have these two in place, now it is possible to define our probabilistic forwarding with coding mechanism. So what is our goal? So we are first of all given the intensity of the random geometric graph lambda. The source has n coded packets, and we are also given this value of k, which is the number of packets that need to be received by any node in the network in order to decode the information from the source. We are given a delta close to 0 and a retransmission probability p. So let's define this RKN to be the nodes within the component of the origin that receive at least k out of the encoded packets. So recall that these are the ones which can decode the information from the source. We'll call these successful receivers. All right. So what are we interested in now? So we are interested in the minimum probability such that the expected fraction of successful receivers is at least 1 minus delta. So it is very close to 1. So delta is a very small number, so it is very close to 1. Notice that the denominator is the number of points within the component of the origin of the graph. Also, so this is the fraction of successful receivers. So RK and GM0 is the nodes within C0, so this is always lesser than 1 because the numerator is a subset of the denominator. Yeah, so what is our performance metric? Our performance metric is the expected total number of transmissions when the probabilistic forwarding is carried out with probability pk and delta. Alright. So one thing to confirm here is that the expectation in both these cases is with respect to both the randomness in the random geometric graph as well as the probabilistic forwarding mechanism. Okay. So a couple of things to remember from this slide. First of all, we'll refer to those nodes which receive at least k out of the encoded packets as successful receivers. Also, I'll say that a near broadcast has occurred when the expected fraction of successful receivers is at least 1 minus delta. Alright. So our aim is to obtain estimates for these two quantities. Yeah, before we go there, let's look at how these two quantities behave. So here I have two plots, one for the minimum forwarding probability, another for the expected total number of transmissions, normalized by lambda times m square. Recall that lambda times m square is the expected number of points within the gamma m box that we choose. Okay, so in each of these plots, I have two curves corresponding to intensities 4 and 4.5. So let's just look at the 4.5 curve, which is the blue curve. The x-axis in both of these plots is the number of coded packets, which varies from 20 to 40. Any node which receives 20 out of these n coded packets is a successful receiver. All right. Okay, so first observation is that the minimum forwarding probability decreases as you increase the number of coded packets. Well, that is easy to see because when you have larger number of coded packets, you can afford to transmit each packet at a lesser probability while still ensuring that you have a near broadcast. While still ensuring that your expected fraction of successful receivers is at least 1 minus delta. So value of delta here I think is 0.1. Yeah. So that is what I mean to say is when you have 30 packets versus when you have 31 packets and you are asking for 20 packets to be received by all the nodes in the network. When you have 31 packets, it's easier because there is an additional packet which can be received as well. So this is what we saw in the initial simulations as well, where we decreased the forwarding probability from 0.8 to 0.72. Okay, so but a far more interesting trend is of the expected total number of transmissions. It initially decreases to a minimum and then increases. So this point corresponding to k equal to n equal to 20, that is the point where you do probabilistic forwarding with no coding. That is the second algorithm I spoke about. After flooding, I spoke about probabilistic forwarding. So that corresponds to this point here. So what this plot is suggesting is that when you do coding along with probabilistic forwarding, you can actually decrease the number of transmissions as compared to probabilistic forwarding with no coding, but at the same time achieve a near broadcast. All right. Moreover, the point corresponding to the minimum here, that is the number of coded packets, and the forwarding probability corresponding to the minimum, those are the parameters to operate the network optimally. That is, at this point you have the least number of transmissions, but at the same time you are achieving a near broadcast. Okay, so our aim is to get estimates for these plots that we have here. All right. Any questions till now? Okay. Uh, okay, so how do we go about obtaining these estimates? So we map the probabilistic forwarding algorithm on the random geometric graph on the finite area gamma m to the probabilistic forwarding mechanism on the random geometric graph generated on the whole R2 plane. Okay, this we denote by this calligraphic G0. Uh, so we'll use ideas from continuum percolation and ergodic theory to obtain estimates of the quantities that we are interested in. Okay. But what is this random geometric graph on the whole R2 plane? How do we generate it? I already told you how to generate it on a finite area. So for this, you can use the principle of superposition of Poisson point processes. What is this principle? I mean, you might have heard of superposition for Poisson random variables. It is similar. That is, if you have two Poisson independent Poisson random variables x1, x2 of means lambda1 and lambda2, then x1 plus x2 will be Poisson lambda1 plus lambda2. So similarly, you have so what we do is we create a tiling of the R2 plane, something like this, and in each of these squares, you generate a Poisson point process of intensity lambda, independent Poisson point process of intensity lambda, as we did before on the finite area gamma m. Okay. Now we add a point at the origin and connect nodes which are within unit distance. This will give you the graph G0. Alright. So this will give you a graph on the whole R2 plane. So this is a way of generating the whole R2 plane, the random geometric graph on the whole R2 plane. Now you can do the probabilistic forwarding on this graph as well. That is, the origin transmits to all its neighbors, Every other node in the network transmits with probability p or does not transmit with probability 1 minus p. Okay. So now we have we have changed our probabilistic forwarding mechanism from the finite area random geometric graph to the whole R2 plane. So now, so what does this theory of continuum percolation now tell us? It says that there exists a critical intensity lambda c such that for lambda greater than this critical intensity, there exists a unique infinite cluster, which we denote by c. Alright, so recall this intensity lambda. So we initially chose the number of points to be lambda times m square. So if this what this statement is saying is that if your lambda is higher than some prefixed critical intensity lambda c, then there will be an infinite component in this in the whole R2 plane, using this random geometric graph that we generated on the whole R2 plane. Inside that there will be an infinite cluster. All right, that is an infinite connected component, which we denote by c. Also, we'll define this percolation probability to be the probability that origin is in this infinite cluster. So this infinite cluster that we have, it can be somewhere else as well. However, so there is a particular, you can define this particular probability that the origin is part of that infinite cluster. Right? That we call the percolation probability. Notice that this probability is with respect to this palm probability, because the origin needs to be a part of the point process in order for you to define this event, that it is part of the infinite cluster. All right. Also, we have the following ergodic kind of theorem. So what this kind of a theorem says is that for lambda in the supercritical regime, the fraction of nodes within a large box gamma m of the infinite cluster converges to this percolation probability. All right. So firstly, so this exact value of lambda c is not known. Moreover, we don't know any analytical expressions for this percolation probability. So here I have, so what this ergodic theorem helps us in doing is we can obtain a plot for the percolation probability using this ergodic theorem. That is, yeah, so the same thing will hold for with respect, if you take the expectations as well using dominated convergence theorem. And using that, you can actually obtain a plot for the percolation probability, which looks something like this. So notice that this graph shows a phase transition at around lambda equal to 1.44, which is the computationally known value of lambda c, or the critical intensity. All right. So we'll use this ergodic theorem in the future as well. Yeah. Okay. So now that we have this particular background, now we are in a position to model our probabilistic forwarding mechanism, which is done using what is called as mark point processes. So what is this? I mean, this is simple. You have this underlying point process phi. For each vertex in that, you associate a mark z. We're taking values in some space of marks. Now z is conditional on phi. It is IID from some mark distribution which we called as pi. So let's take an example of the single packet probabilistic forwarding. So in the single packet probabilistic forwarding, each node, so there is a single packet, so each node either decides to transmit the packet or not. So you can associate each vertex of the random geometric graph with a Bernoulli random variable taking value 0, 1. So all the yellow nodes here are those which decide to transmit the packet and have mark 1, and the red nodes are those which do not transmit the packet and have mark 0. All right. So using another property of the Poisson point process, this can be thought of as two independent Poisson point processes of intensities lambda p and lambda times 1 minus p. So you can split it as all the nodes with mark 1 and mark 0, which we denote as phi plus and phi minus respectively. So the transmitters are all those nodes within the component. So all the nodes in this phi plus point process are the transmitter, are the ones which decide to transmit the packet. But the actual transmitters are those which receive the packet from the source and then transmit it. And hence, all the nodes within the component of the origin within this phi plus point process are the ones, are the transmitters of the packet. What about the receivers? The receivers are, although first of all the transmitters are of course receivers because they should receive the packet in order to transmit it. Along with these, there are also nodes in this phi minus point process, all those red nodes, which are adjacent to nodes within the C component of the origin of the phi plus point process, that is the C0 plus. If you recall the initial simulations that we had, these are all the blue nodes that we have. So these nodes in phi minus adjacent to C0 plus, those are the blue nodes that we had initially. So this together we call this the extended cluster of the origin and then denoted by C0x. Also, if the intensity of the phi plus point process lambda p is greater than the critical intensity, then there will be an infinite cluster in the phi plus point process, which we call it as C plus. The extended cluster of this infinite cluster of the phi plus point process, we call that to be Cx, or the infinite extended cluster, or IEC for short. Okay. So this is how we model the single packet probabilistic forwarding as a marked point process. Similarly, you can model n packet probabilistic forwarding as well. So in this particular case, you associate each vertex with a tuple z1 to zn, taking values in 0, 1 to the n corresponding to each packet transmissions. So since each packets are transmitted independent of each other, conditional on the underlying point process, so zi's are independent Bernoulli P for all I. Alright. Okay, so now with this we can state some of the main results. So recall that we were interested in obtaining estimates for the minimum forwarding probability. Is the probability that the expected fraction of successful receivers is at least 1 minus delta, and the expected total number of transmissions at this minimum forwarding probability. So let's first look at the expected number of transmissions. So what this is saying is, if lambda times p is greater than the critical intensity, then the expected total number of transmission, this lambda times p is the intensity of the phi plus point process. So when the phi plus point process has an infinite cluster, then the expected total number of transmissions is given by this expression. So let me try to break this up. So expected total number of transmissions is n times the expected transmissions of a single packet. So if you look at the probabilistic transmissions of a single packet, if the origin is in the infinite cluster of the phi plus point process, recall that happens with probability given by the percolation probability, but for the thin process of intensity lambda p. So that is theta of lambda p. So that is this term here. Now, given that the origin is in the infinite cluster of the phi plus point process, what are the other transmitters? The other transmitters, as we discussed, are all those nodes in the component of the origin. But the component of the origin is nothing but the infinite cluster of the phi plus point process. And hence, the other transmitters are the fraction of nodes within the infinite cluster of the point process. And that is again by the ergodic theorem applied to the thinned point process of intensity lambda p is given by this expression here, which is how we obtain this expression. A similar analysis holds.
Vinay, this is 1 second.
Yes.
So, can you repeat this last point about how you got the other theta of lambda p?
This one?
Yeah, that one.
Yeah. So, okay. So first, let's assume that the origin is in the infinite cluster of the thin point process phi plus. Okay.
Yeah.
So if the origin is in the infinite cluster, what are the other transmitters? We already saw that the other transmitters are the nodes in the component of the origin of this phi plus.
Yeah.
Right. Now, if the origin, so component of the origin if phi plus is nothing but the infinite cluster, because we have conditioned on the fact that origin is in the infinite cluster of phi plus. Now, okay, so now basically what we want is the number of nodes in the component of the origin of phi plus, number of nodes in the infinite cluster of phi plus, but number of nodes in the infinite cluster of phi plus. So if you look at the fraction of nodes in the infinite cluster of phi plus, so that will be from the ergodic theorem, that is nothing but equal to theta of lambda p, because theta of lambda p is the percolation probability from the ergodic theorem that we had. So this additional term that we have is nothing but the number of nodes within some large box gamma m, So
Yeah,
lambda
that is
times p
fine.
times m
So
square.
n times lambda times p m square, that is fine. It's
Uh,
just that the first argument that you made for theta of lambda p, you were arguing about it from the perspective of the origin being in an infinite extended cluster, right?
uh,
The second thing was from the viewpoint of the infinite extended cluster of the 5 plus point process.
Infinite cluster, not extended cluster, infinite cluster.
Infinite cluster. Okay. So how did those two expressions come out to be the same?
That is because of our ergodic theorem.
Okay.
Let me go back to that, perhaps. Oh, sorry. Uh, where was that? Yeah. Yeah. So this ergodic theorem that we have here. Now think of the C to be C plus, the
Yeah.
infinite cluster
Okay.
of the phi plus point process.
Okay. 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 Got it.
So
Yeah.
you have this will be lambda times p, and this will be theta of lambda p.
Yeah. Fine.
So
Okay.
it's for large m, the fraction of number of nodes in the C plus point process is lambda times p times m square times theta of lambda p.
Yeah. Yeah. Okay.
That is what you have.
Thanks.
That is what I had there. Yeah. Yeah. So okay. Similarly you can obtain expressions for the expected fraction of successful receivers as well. So first of all, you divide the numerator and denominator by lambda times m square. So denominator would be the fraction of nodes in the component of the origin of the original point process of intensity lambda. So that is given by the theta of lambda. Now, so what about the fraction of successful receivers? So these are first condition on the fact that origin is in the infinite extended clusters indexed by some subset t out of the n packets of cardinality t, small t. Okay, so given that origin is in the infinite extended cluster indexed by these t only, then what are the other receivers? The receivers are all those nodes which are in at least k out of the t infinite extended clusters. CKTX actually, yeah, CKTX. Now, from a similar ergodic theorem that we had, that would be equal to the probability that origin is in at least k out of the t infinite extended clusters, which is given by which we call the t packet extended probability, and denoted by theta ktx. But however, note that packet transmissions are not independent. They are only independent conditional on the underlying point process. And hence, it's not easy to obtain exact expressions for this. You can obtain some bounds, but not the exact expressions. But if you indeed assume that these packet transmissions are independent, you can obtain some mean field heuristics kind of mean field heuristics, which look and you can obtain simple expressions, uh, which gives you this tail binomial kind of probability, which can be used to compare it with the simulation results. So here I have the simulations along with the expressions obtained using this. So notice that the minimum forwarding probability from the estimate tracks the original expression pretty well. However, the expected total number of transmissions, there is a deviation. So this deviation can also be explained. So then notice that there's a small difference between these two plots. Now, as you increase the number of coded packets, your peak and delta decreases. So this lambda times p decreases and it approaches lambda c, which is the critical intensity. And you saw in the plot of the percolation probability that there is a steep phase transition around lambda c, and hence when you plot the same using this, this small difference gets blown up, and this I mean you see this divergence happening. But however, notice that what this justifies is that compared to probabilistic forwarding, which was corresponding to this point here, by introduction of coded packets, you can actually decrease the number of transmissions while ensuring a near broadcast. So that is what it justifies. However, we have not been able to characterize this exact minimum that we have here. This, you can actually from this plot you can actually show that this actually decreases and then increases, but the minimum occurs somewhere else. So we don't have any relation relating these two. Okay, so with that, I can end the talk. So finally, what we have is we proposed a new mechanism, broadcast mechanism, probabilistic forwarding with coding. We obtained estimates for the minimum forwarding probability and the expected total number of transmissions. Also, we also used heuristics to conclude that introduction of coded packets with probabilistic forwarding reduces the number of transmissions while ensuring a near broadcast. And this is also true for many other graphs such as grid static structures as well, if the graph is well connected. Yeah. So with that, I'll end the talk and I can take any questions if there are there. Thank you.
Thank you, Vinay. Uh, Participants can ask question directly by unmuting themselves or they can write in the chat.
Yeah, this is a
Questions?
slightly
Yeah.
unrelated thing, but I mean, I'm not. I actually joined the talk late, so Vinay, there was this thing on fountain codes, rateless codes that you had said at least long time back.
Uh-huh.
So uh, see, there I mean, um, you're streaming bits one after another, right? In the sense that um, you form random linear combinations of the sort of the information bits that you have, and then you send as many as are required in order to guarantee k successful transmissions at the
Hmm.
k successful receptions.
Hmm.
So how do you think this fits into that perspective, instead of trying if fountain codes can be used in such transmissions on well connected graphs?
Hmm.
uh, what do you think again is the relation between those two? Because I didn't get that clearly still. So
Okay. Um, so usually, I mean, so from what I have gathered is so from fountain in fountain codes. So you're making this. So the source initially has some KS packets there,
yeah.
and every what it does, it takes linear combinations of this and sends over the channel.
Mm,
Now, any node in the network which receives some k out of this some k packets, it's able to decode the ks information in the ks data packets.
yeah.
So this k is usually greater than this ks. But usually the way it is employed in practice is that I mean, you can't be just sending things all the time. So as long as, I mean, you can do that as long as all the nodes in the network receives, but that will require some kind of a centralized mechanism. So usually how it is employed in these actual communication systems is that you encode this ks into some fixed n, which is larger, is
Yeah.
much larger, and then you transmit them, and whichever is able to decode, they'll whichever receives k out of these n, they'll be able to decode the information in the ks data packets. So that's how it's usually employed. I mean, that's what I got from looking at some of the literature on fountain codes. So yeah, so that so now in that scenario you can actually so for me this ks does not matter, it's only the k that matters.
Mm.
So you can actually use that in this, using this probabilistic forwarding with coding mechanism as well. That is what you were asking, right?
Yeah. No, it's just that I still see coding onto a fixed block length n and then transmitting and letting the block length go to infinity is the usual way. But now, I mean, that is what you have employed too. But
uh,
rateless codes came in order to circumvent this issue of, I mean, it's rateless in the sense that there is no block length at all, right? There's no n at all. And
hmm,
so you can do some sort of sequential transmission.
yeah.
Okay.
uh,
I mean, can how
uh,
do you reconcile these two things? I mean, why don't you just try using a similar rateless code over, your in your model as well? Why do you need to use an MDS code?
No, I can always, I can use this rateless code which has this property. So I think, I mean, as far as I know, the rateless codes that I know of have this property that any node which receives k out of n will be able to decode. So you can always use, but yeah. So in terms of yeah, there I yeah. So you are asking how do you? So in this work, I have actually not considered any.
Yeah,
Uh,
yeah, I understand. So
data.
in this model, it's the k out of n, the MDS model.
Uh,
But
no,
suppose you were to put in, yeah,
no, that is also true. Fountain, you can use fountain codes here as well. What is wrong with it? Only thing is, I mean, I mean, there are network coding mechanisms which actually do this in the sense for broadcasting. Every intermediate node can also combine packets and then forward it. Things like that are there. So those employ fountain codes
oh,
which
I
are
see.
used in broadcasting.
Okay.
Yeah.
No, I still don't get the relationship between, uh, I mean, I don't see how, uh, okay. Because, I mean, I don't see how fountain codes can be used in the first place here. You're saying that the only parameter that matters is the k, that you can essentially get rid of the n dependence, is it?
No. Independence is there. So that's what. So that I mean, the way it is done practically is that even though they say rateless in practical wireless system, what you do is you encode it into some large n. You transmit some large n linear combinations,
Yeah, fine. Okay.
and then you ask for k to be received.
Fine.
Yeah. And you work with that. That's it.
Okay, good. Yeah.
Yeah. Any other questions?
Are there any more questions? All right, then I think we can end the first talk.
Thank you.
Uh, Thank you, Vinay, for the talk. And on behalf of IEEE-IISc ComSoc and SPS, please accept this memento. And we wish you all the best for your future endeavors.